guys are fantastic. Their careers have been exceptional. And now, as they work here at InfoAge to do research, historical research in particular, they have found some information about what Edwin Armstrong did to create the transmitter that made it possible for the moon bounce to have happened in 1946. So please let me turn over this meeting to Ray Chase and to Al Klase. And can you please unmute yourself? I'm going to go ahead and unmute you.
Well, I was able to unmute myself. I assume you can hear me.
I can hear you. I'm asking Ray to unmute himself. Ray, can you unmute?
Yeah, I'm unmuted. I'm fine. I can hear everybody.
Okay, you guys go ahead and take over.
Okay, I'm the primary presenter, so I will need to share screen.
Okay. Here we go. I just want to warn you that if a participant comes in, you'll receive a message to admit them. Please admit them. Okay?
Roger.
Here. It's all yours.
Okay. Okay. My name's Al Klase. I'm N3FRQ. I'm a member of the New Jersey Antique Radio Club, and in turn, we're a supporting organization for InfoAge, and we run the Radio Technology Museum on the main campus here at InfoAge. Today, I'd like to talk about our favorite radio inventor, Edwin Howard Armstrong. He was born in New York. A few years later, his family moved up to Yonkers, nice big house. When he was about 10 years old, his father was in publishing, brought home the Boy's Book of Inventions. And Howard read about Marconi in there, and it inspired him to a life in radio. He went so far as to build a 120-foot mast in their backyard, flew kites to hold up antennas and such. And eventually he attended Columbia University as an EE student, rode down there on a red Indian motorcycle on a daily basis. Now, most of what we're talking about today depends on vacuum tube technology. I mean, today everything is transistors and integrated circuits, but this was the electron device technology of the day. And in fact, in Armstrong's day, it just barely existed. A guy named Lee DeForest had invented the 3-element vacuum tube. You have an evacuated glass tube. You have a hot cathode at one end, plate at the other end, battery outside and the load, so you have a current flowing here. And Armstrong's addition to this technology was known. There were things like it was known as the Edison effect, but Armstrong's addition was to put a grid in here. And so when you put rather DeForest contribution, so a small signal on the grid will either encourage or discourage the flow of electrons. And what this does is control energy from a local battery, so you can make a small signal into a big signal. This was very primitive at the beginning, but on through the years, this becomes the basis for radio and television and computers until the transistor is finally invented. So in 1912, Howard gets a DeForest Audion, and he builds a radio out of it. And there's sort of a block diagram down here. You have an antenna and a tune circuit, and the Audion, which is a detector and an amplifier. And what Armstrong developed was a circuit where he added feedback from radio frequencies from the output of the amplifier back into the input circuit. And what this does is, if you look at this schematically, you've got some resistance out there, which is unavoidable. But the energy coming back cancels out the resistance, and the response of the circuit gets better and better as you increase the amount of feedback. You get to a point where the resistance is completely canceled out, and then the circuit oscillates, becomes a transmitter, a generator of radio frequencies. So this resulted in a superior radio receiver. It was 20 or 30 dB more sensitive than the DeForest Audion, just in a simple circuit. But perhaps more important, it's the first electronic oscillator. And that allowed a couple of things. First of all, it allows heterodyne detection of CW signals, which was very difficult to do before this time. People would be running Alexanderson alternators to be the BFO in their receiver. It also allows you to build a small and portable and practical continuous wave transmitter. So this is the beginning of the end of spark telegraphy and really the beginning of the electronic age. Now, there's a tie into info age here. In 1914, Armstrong had his patent in place and was revealing the feedback circuit to the world. And he ends up doing a demonstration to the Marconi company. Their big receiver site was now the InfoAge site today, Marconi Belmar. And he goes down there to do a demo, and the person that Marconi brings in to be their radio operator is Dewitt Sarnoff, who later becomes a big wheel in the Radio Corporation of America, which is established later on. The site was under construction. There's a picture down here at the bottom from 1914. This was the operations building, but it was under construction. There was a shack construction shack outside, and Armstrong and Sarnoff sat there all night playing with Armstrong's radio, which was far and away more capable than the Marconi radio they were comparing it to. The two men became fast friends. Now, a couple of other things that happened in that particular time period. He also does a demonstration to AT&T and their chief engineer, J.J. Carty. AT&T took a formal disclosure from Armstrong, and they went silent on him. They went off and invented modern radio. Guys with names like Heising and Colpitts and Hartley did their thing. He also became locked in a long-term battle with Lee DeForest, the inventor of the Audion. DeForest, of course, claimed that he invented the feedback circuit, which, of course, was completely bogus. So the feedback circuit ultimately leads to radio broadcasting. KDKA in Pittsburgh goes on the air at the end of 1920, broadcasting the election results. Radios in the home become commonplace. In fact, this is a Westinghouse Armstrong licensed regen, ladies listening here. But to use a radio like this, you had big antenna in the backyard. But this just became a complete fad. Everybody had to have a radio. So shift gears a little bit. War clouds are gathering. United States enters World War I in 1917, and there was a lot of patriotism afoot here, and there was also elements of the industrial military complex. The phone company was going to sell a lot of stuff to the Signal Corps, and J.J. Carty, who we mentioned, puts on a uniform and becomes the chief signal officer, and he recruits thousands of people out of industry to join the military and support the technology there. And one of these people, and I don't know if there was direct personal contact, but Armstrong at this point was fairly famous for the feedback circuit, not rich, but famous. And he and Carty knew each other. Armstrong volunteers. He gets a letter, says, effective immediately, you're captain in the Signal Corps. 2 weeks later, he gets another letter that says, go over to Hoboken and get on the ship. You're going to France. And in France, Carty had helped set up a thing called the Division of Research and Inspection. They rented a mansion in Paris that had some space behind it. He put $100,000 in lab equipment in wooden crates that could be made into workbenches. And so in effect, what you had was an AT&T research laboratory in Paris, where Armstrong was assigned to be the head of the aircraft radio section. And while he was there, he solved a number of problems, but one of the problems was high frequency reception. The existing technology, was hardly good to a megahertz. And they wanted to do some work up around 3 megahertz. They thought maybe they could detect enemy aircraft by listening for their ignition noise. And so what Armstrong comes up with, he leverages his knowledge of heterodyne frequency conversion, which of course he was familiar with from the regenerative receivers. But instead of converting the incoming signal down to audio where you could hear it, he converted it to a lower radio frequency, ran it into a French amplifier and filtered it at 100 kilohertz and created a really sensitive radio. He named this the supersonic heterodyne receiver. In the old days, they used the word supersonic the way we would use ultrasonic today. So this is the super heterodyne circuit. And yeah, we're still using this technique today. You're carrying around about 4 of these in your cell phone. So on into the 1920s, Armstrong comes back to civilian life. He's hypothetically working at Columbia. And his old buddy, David Sarnoff, buys his super heterodyne patent and another patent for a whole bunch of money, makes Armstrong rich. Armstrong also courts Sarnoff's secretary, Marion McGinnis. There's this famous episode of him clowning around on an RCA tower and sending the pictures to Sarnoff's office. And he is working with RCA to develop the first commercial super heterodyne receiver. And he gives the prototype of that to Marion as a wedding present. By the way, a good read on Armstrong and Sarnoff and DeForest is the book Empire of the Air. If you haven't read it, do so, or see the video. Just quickly, here's Marion and Howard on the beach with the super het. And the important thing about this radio is it was sufficiently sensitive that it could operate without an external antenna. There's just a loop in the back of that box, works just fine. It's a portable, you can tell it has a handle on it. Of course, it weighs about 40 pounds, loaded down with batteries. So that was a great success for Armstrong, his second great invention, the super het. And moving on into the 1930s, he develops wideband frequency modulation. Now, there was a lot of AM activity, a lot of CW activity, but a persistent problem with AM was in old terms static, lightning, and there was a lot of man-made noise. I mean, every automotive engine put out a lot of ignition noise. There was no suppression of that. And simple electric motors with sparking commutators did the same thing. So Armstrong does a lot of work to develop wideband frequency modulation, which beats the noise. No static at all, as the Steely Dan song says. And it does a couple of things. in addition to getting rid of the noise, this happened at high frequencies up in the 40, 50 megahertz range for starters, wide bandwidth, and that allowed high fidelity transmission, which would eventually take in stereo. He did his early experiments about 1933 from the RCA TV, experimental TV transmitter site on top of the Empire State Building. However, his relationship with Sarnoff turned ugly. So in 1935, he went off and built his own laboratory and radio station. By the way, this is guys from GE about 1940 demonstrating their FM radio in front of this huge spark, and they managed to clearly hear FM signals, while of course AM was completely wiped out. So Armstrong's facility at Alpine. Now, Alpine is in northeastern New Jersey, right by the Hudson River. This is, if you know the area, this is 9W here. The site is about 500 feet up out of the river. He builds a 450-foot tower so he could put a big signal down into the New York City area from here. A nice brick laboratory and transmitter building down here at the bottom. So FM changes home radio once again and brings hi-fi sound into the home and encourages the whole hi-fi phenomena. So FM's becoming a going thing, and then World War II breaks out. And so a lot of things just sort of go on hold. But Armstrong, and remember it's Major Armstrong, he has a strong feeling for the Signal Corps and such things. He'd been actively working with the Signal Corps on FM two-way mobile radio since about 1939. That was based on some work he'd done with the Link Corporation, building radios for the Connecticut State Police. And this development leads to the best mobile radio system of World War II, which turns out to be really important when you're talking about mechanized warfare. FM was also used for carrier multiplexed radio relay systems. You put multiple telephone circuits down a single radio circuit and save a lot of trouble there. He signed his patents over to the Signal Corps and the government for war purposes. And he took a contract to develop FM radar. He thought he could extend the range of radar using FM techniques based upon the range and noise resistance he was getting out of the wideband FM broadcast things. So this is the building at Alpine. The big tower is off to the right here, but he installed a SCR 271 Army radar tower there, an antenna, and built electronics to implement his FM radar scheme. Now, just a quick review of radar. You have a directional antenna, and you send out pulses, and you listen for the echoes. Typically on an oscilloscope, here's the main bang, the transmitter pulse, and sometime later over here, you get a reflection from the target. In normal pulsed radar, these pulses are very narrow, and the duty cycle is considerably less than 1%. So the amount of energy involved is limited, and that places some limitations on how well your radar can work. We don't know a lot about Armstrong's FM radar. It was a classified project. It was during wartime. And what we do know comes from his patent application from 1947, which was really pretty thorough. You could almost rebuild one of these from the patent application, but who would really want to? I threw the block diagrams in here just sort of to point out each one of these blocks represents a vacuum tube and the support circuits to go with it. So this thing was fairly complex. And what he used in the transmitter was sort of the same wideband FM scheme that he used in broadcast, except it was modulated by a variable audio oscillator and keyed on, and the transmitter was keyed on and off on alternate cycles of that modulation. And now so he had a fairly large amount of energy going out with a 50% duty cycle. And then to improve the receive situation, he built a very narrow band receiver. In fact, a quadruple conversion super heterodyne. We'll talk about that in the next slide. And it's frequency locked to the transmitter. It gets its local oscillator signals from the transmitter. So here's how it worked. Here we have frequency and time. Of course, in an FM transmitter, you have a carrier frequency, and the modulation changes that frequency one direction and then the other. And in this case, it was 200 kilohertz in each direction. This was quite a wide signal. So he turns the transmitter on for one cycle of the modulation, turns it off for a cycle, back on for a cycle. So if you have this transmitted signal hitting a target that the return time is the same as the cycle time here, when you turn the transmitter off, that received signal will be here sort of following the same path. And his receiver, which is very narrow banded, tracks that frequency. So case A here, where the target is one cycle out, one cycle distance, the receiver hears it. If the target is not at that distance, the receiver doesn't hear it. So he hoped that between high average transmitter power and narrow receiver bandwidth, he'd be able to extend the range of radar. Our analysis of this is that this probably worked, but it's subject to some serious limitations. One is that you still have the problem that you're working with line of sight, so you can't see down over the horizon with it. So you don't have a great advantage over advanced pulse radar. And also, the operation was probably cumbersome because apparently you had to tune that audio oscillator for the modulation. Is there a question? You had to tune that audio oscillator to find the target. So target acquisition was probably really slow.
Right. Well, this afternoon, I'm going to look online and see if there's any more information.
Maybe tonight something will come out.
Hello, there's someone out there who is.
Yeah, it's I think it's Alan, Lori. Lori, if you make me the host, I can take care of this. Sorry to interrupt, Klase.
Yeah, that's okay.
Interruption, not sure what that is. Hold on.
So anyway, the Signal Corps pretty much dropped this project after World War II, and there's a lot of confusion about Armstrong's relationship to Project Diana. We'll go into that here and try to straighten some of it out. There's pronouncements that that the moon bounce was done with FM radar. No, that isn't true. And Armstrong FM radar died out. There were later radar systems that used FM techniques, but they were distinctly different from what Armstrong was doing. So one of the first issues we had to face was there actually Armstrong radar at Camp Evans at the Diana site? And because we looked at all the contemporary articles on the moon bounce and the word Armstrong never appears. A little later on, Dr. Harold Zoll who was director of research at Fort Monmouth and one of the real heavies in radar development, wrote a book called Tales of Government Scientists. And in there, he says in so many words, Major H. Armstrong had been working on a very high-powered radar set, which was set up in the Evans area at Fort Monmouth. And then he mentions that Jack Dewitt later on modified it to do the moon bounce. So we know that we're taking that as fact. And so it was Armstrong equipment. Let's take a look at John Dewitt. Interesting character. Guy was a ham radio operator since 1921. He's about 15 years old. This was in the Nashville area. He gets an EE degree from Vanderbilt University. He works for AT&T for a while. And then he goes to work for WSM, the big AM station in Nashville. Think Grand Ole Opry. And he also had a side interest in astronomy and ham radio, of course. And the date I had was 1940, and it was interesting to see those pictures of their attempt at moon bounce in the late 1930s. So he's thinking about and actually trying to do moon bounce. War breaks out. He joins the Army. They make him a lieutenant colonel because of all his experience and capabilities. And he eventually becomes the director of the Evans Signal Laboratory, which is Camp Evans and the Diana site. And so now the war's over. He wants to do moon bounce, and he runs the Army Radar Laboratory. So, you know, what an opportunity. So is born Project Diana. Diana's the Roman goddess of the hunt and the moon. I had a lot of trouble finding a picture of Diana properly attired, but there she is. And this was mentioned a little bit earlier, but the basic team was Colonel Dewitt as leader and King Stadola as chief scientist, Harold Webb, Herbert Kaufman, Jack Mosley. I'm sorry?
Toddler.
Thank you.
Yes.
I needed to get straightened out on that. There's an old Czech folk song where it's Stodola Pumpa. Stodola means barn in Czech, but that's another story. So that was the team. And Dr. McAfee gets involved in this because, of course, he's the master of things like the radar equation. And there are several factors that go in here, like transmitter energy, receiver sensitivity, how good your antenna is. You can't do much about target reflectivity, but maybe you want to calculate that out. Now, the basic problem here is you're fighting what's called the inverse square law. Signal comes out a mile and its energy is distributed across some area, comes out 2 miles, now it's distributed across 4 times the area, 9 times, etc. And now this happens to you twice, once going out to the target and again coming back. So we end up with this thing being a 4th route in here, which means any change you make here is going to be real tiny. You're going to have all your ducks in a row to make this work. So energy is power times time. So you want to keep the transmitter on as long as you can. And part of receiver sensitivity is also its selectivity, so you don't have to listen to the noise. So those were the problems. So how did they do it? Well, to maximize the antenna gain, they already had the SCR 271 radar up there, but they put a second antenna side by side. That gets you 3 dB improvement in the antenna. they needed high average transmitter power. Now the pulsed transmitter in SCR 271 wasn't even going to come close. But they had Armstrong's transmitter sitting there that could do 4 kilowatts CW. And so long pulses weren't going to be a problem there. It's also crystal controlled, so frequency accuracy is going to be good. And they had Armstrong's narrow band receiver, so they could go to narrow bandwidth and beat the noise. The receiver has to be accurately tuned to the transmitter, but Armstrong's already was. They made some modifications to it so they could tune it plus or minus 300 hertz to take care of Doppler shift. So that's what they do. Now, this scheme was going to be pulsed radar. FM had nothing to do with it. They disabled the FM modulation in the transmitter. So here's the classic picture of the Diana antenna looking at the moon. The individual elements were, this is 110 megahertz, so the elements were so big. And the basic SCR 271 was an 8x4 array of dipoles in front of a reflector. And they hung a second one up here, making it an 8x8 array. So that's a 3 dB improvement, which doesn't sound like a lot, but it's the same as doubling your transmitter power. This is almost the only piece of SCR 271 they actually used beside the antenna. This is the control console, which involved the antenna control dials and controls there. And this was kind of haywire. You see a lot of extra stuff hanging around here. The transmitter was a pretty easy modification to Armstrong's transmitter. Typical Armstrong FM, you start with a low frequency crystal oscillator, about 500 kilohertz, and you multiply your way out to, in this case, 111.5. And so that's out to your transmit receive switch. And this signal also comes out to control the radio frequency. Got some pictures here. You see Herb Kaufman adjusting the high level multipliers in the transmitter. And here's Jack Dewitt, taking a look at the transmitter. Now, this was another source of confusion. The actual transmitter appears to have been the Armstrong transmitter. And we know this from some of the articles that were published in 1946 by the members of the team. This was Mofensen in electronics in 1946. And we see that the output amplifier uses vacuum tubes called 6C21. And they look like this, and that is indeed what's in this box here. And that'll get them about 4 kilowatts output. And that's what they used for the initial experiments early in 1946. Now the confusion comes in because shortly thereafter, they decided they wanted more transmitter power. They did take an SCR 271 transmitter, which has a pair of water-cooled triodes in it. However, the transmitter was a free-running oscillator, and that wasn't going to work for moon bounce. So they modified it to be an amplifier and attached it to the output of the 4 kilowatt amplifier. And this data comes from proceedings of the IEEE in March 49. So the output of the transmitter was increased to 15 kilowatts. I know there's a reference somewhere that says 50 kilowatts, but that apparently wasn't the case here. And a lot of the confusion arrives, because here in April of '46, where Dewitt appears on the cover of Radiocraft magazine, he's in front of the SCR 270, the modified SCR 271 transmitter. So, you know, there are accounts that say that's what they used for the initial experiment. We don't think so. That was later on. The receiver, quadruple conversion super heterodyne. Now, to go back to the super heterodyne, signals come down from the antenna. They get to a mixer, which is a non-linear circuit, and you inject a local oscillator signal. You get beat products that come out over here. And usually you take a high frequency, you convert it to a lower frequency, a fixed lower frequency, where it's easier to amplify and filter it. Now, you can't go all the way down to a very narrow bandwidth, at least in those days you couldn't directly. So we make 4 frequency conversions. First intermediate frequency being 32.5 megahertz. They got a bandwidth of a megahertz there. Second conversion gets you down to 6.7 megahertz, about 200 kilohertz bandwidth. Third, down to 6.5, maybe 50 kilohertz bandwidth. And then finally, all the way down to audio to 180 hertz with a 50 hertz bandwidth. So these first 3 conversions, the local oscillator frequencies are derived from the transmitter. So this thing tracks the transmitter. Now, they had this problem of Doppler shift because the moon has a velocity relative to Earth. I think it's maybe a couple hundred miles an hour. And with a bandwidth this narrow, you have to compensate for that. So this 4th oscillator was again a crystal oscillator, but it was variable. They had a crystal holder that could change the capacitance of the crystal. And so they could tune about plus and minus 300 hertz here to be precisely on the return signal. So all of that put together, well, here's Stadola and Webb. Webb has his hand on the fine frequency control for the receiver. We weren't real sure just what this stuff was or what it looked like, but this is a picture of some Armstrong equipment that the Columbia people have. This stuff was at Alpine. It was really unidentified, except that this was a transmitter, this was a receiver. But if you look at these doors here and these doors over here, this sure looks like the Armstrong receiver as Armstrong built it. And like I say, there's the crystal holder with the variable frequency to do the fine tuning. So 10 January 1946, they have their first success. Here was a picture off their long persistence 8-inch oscilloscope. Here's the trailing edge of the quarter-second pulse here. I guess they had some local reflections here on Earth, but 2.5 seconds later, they get a nice pulse back from the moon. So they did the job. And as somebody pointed out earlier, these QSL cards were from later on. They continued doing moon bounce experiments on through the 1950s with more power and higher gain antenna, et cetera, et cetera. And at some point, they started issuing QSL cards. But so Project Diana moon bounce experiment did not use FM radar techniques. Absolutely not. But it did heavily depend on Armstrong designed hardware. One last slide. Meanwhile, back at Alpine, and this story comes from a gentleman named Ren McMahon. He later becomes famous at CBS, but he worked at Alpine in the late 40s. And He recounts that this was an audio recording while he described some color slides he had taken. And he says that REL, that's Radio Electronic Laboratories, they're out in Long Island, they were closely related to Armstrong, was busy building a copy of the transmitter we have over here. That transmitter Armstrong paid for and gave to Fort Monmouth, which gave it to, there's something signal laboratory down there. That would be Evans Signal Laboratory. And then Wren tells the story, and so it's possible that while the modifications were going on for Project Diana, that they were working with the Alpine people to get the modifications made properly, and the system at Alpine may have been modified in parallel. However, Wren tells the story that he suggested to Armstrong that they range the moon. And he says Armstrong was usually a pretty easygoing guy, but he got real stern, and he says, Rennie, we're not going to do that here. Don't aim that thing at the moon. Don't let me catch you doing it. And so Major Armstrong was leaving all the credit go to the Signal Corps. And that's pretty much my story, and I'm sticking to it. Let's see, I guess I'll stop share. Well, let me keep share up in case there's questions that involve some of the slides, but if there are questions, I'll take them now.